Hello and welcome to the first session in our Nastran InCAD series. My name is John Twardock, and I'm a member of the Simulation Global Channel Enablement team. This presentation provides a high-level overview of simulation, with a specific focus on the discipline of mechanical simulation. The intent here is to provide you with a basic knowledge of mechanical simulation so that you can better understand and capitalize on the opportunity that Nastran InCAD presents. The three main topics we will cover today include what is simulation, why are customers using the technology, and what type of problems can be solved with Autodesk simulation. It's good to begin our discussion with a proper definition of simulation. Here you can see the Britannica version, which defines simulation as a research or teaching technique that produces actual events and processes under test conditions. They further state that developing a simulation is often a highly mathematical process. Well, let's apply this definition to product design and view it from a timing perspective. When the FEA method was first introduced as a means of performing mechanical simulation, the technique was applied to reproduce results from an event that had already taken place. That is, something that already happened in the past. This certainly proved to be a valuable tool for determining what went wrong following a design failure, but in a sense, it was originally used as a study that was forensic in nature. As computing power grew exponentially and software technology evolved, engineers adopted a more proactive approach to applying simulation. This comes from the realization that it's far more cost-effective to use simulation as a prediction of how a design may perform in the future, rather than as a means to reconstruct why it failed. This upfront approach provides the greatest return on investment and also leads to dramatic design innovation. When we apply the concept of simulation to engineering design, the most common methodology in use today is called the finite element method. This is a mathematical technique that is used in Autodesk software. It takes a complex shape and divides it into smaller, simpler blocks called elements. The method then solves a simple formula at each element, combines the answers together to yield a result for the entire object. The results can be viewed numerically or better yet displayed as a color contour plot, shown here at the bottom right. The goal of mechanical simulation is to predict things like stress, deflections, thermal loads in a structure or component. We want to do this because too much stress or deflection can cause the structure to fail. There are three key user inputs required when solving mechanical simulation problems. They're shown here as the blue boxes we'll be building on the left side of this workflow diagram. First, a geometry representation of the design is needed. This is usually developed using a 3D CAD system, such as Inventor or SolidWorks. Most of you are quite familiar with this type of computer-aided design and have seen impressive models developed using Inventor. Once the geometry is completed, the user must define what type of materials are being used in the design. For example, is this object made of steel, aluminum, or a specialty composite? Each of these materials have different properties that define how much they will resist or bend when forces are applied, so it's important that accurate material data is used. Finally, the third input required is the operating loads or boundary conditions. In this step, the user can place different forces and loads on locations in the design and also indicate what regions of the geometry are constrained or restricted from movement. Think of the simple example of a chair. The load may be 500 pounds of force applied in a downward direction to the seat, while the constraint tells the program that the bottom of the chair legs are sitting on a solid floor and therefore can't move downward and they will resist the force. Once the geometry, material properties, and operating conditions are set, the problem is submitted to the InCAD solver, which in our case is Nastran. The solver then calculates the stresses and the deflections for each element, reassembles them, and provides predicted values for any part of the geometry. Using these answers, the designer can then check his results against desired performance. The beauty of doing simulation on a computer is that it's a very repeatable process, and the user can change input variables to see how they affect the result. This means you can play many what-if games and try different geometries, different materials, or even different load cases, all without building a physical prototype. This significantly narrows the scope of testing and also allows for much greater innovation. Traditionally, when users discuss simulation, they tend to speak in complex terminology that describes the mathematical parameters of the simulation process. Don't allow yourself to be intimidated by these terms. We've aggregated a glossary of common simulation expressions for you in one team source, along with a simple, straightforward definition to help you understand their meaning. It's important that you realize, while these terms are useful to the engineer, they're much less relevant to the executive management at your customers. When we discuss simulation at Autodesk, our focus is on the benefits rather than the technical features. Simulation is all about creating better designs so that your customers get products to market faster, which are lighter, stronger, higher quality, more reliable, and more innovative. Let's look at how simulation fits into the traditional design process and explore further why your customers should be using it. Well, why do simulation? It's important that you can answer this question for your customers, especially those who are not using simulation today. Traditionally, design engineers have made physical prototypes and destructively tested them to see how they perform. This is generally expensive and time-consuming. Let's take a closer look at the issue. In most cases, your customers' products are required to pass industry-defined tests in order to be accepted for commercial release. Testing requirements may be driven by government or industry regulations and often focus on improving product safety and reducing liability. Some common test types include strength, thermal, vibration, fatigue, and crash or drop shock testing. In all cases, these tests require complex equipment, monitoring, and setup, which takes a lot of time and is expensive. If a product fails, it may be many months before a new design can be developed, prototyped, and retested. The traditional design process relies on creating a design, building a physical prototype, testing the prototype, and then fixing whatever problems arise. The expression "back to the drawing board" was commonly used to describe the frustration of prototype failures. Design engineers have built up tremendous experience over the years and may rely solely on this test and break method to create a good design, but it's very unusual that only one physical prototype is made, and it often requires several loops of this design, test, and fix process. It's not only costly, but also increases the amount of time it takes to get a product to market. Contrast that with a digital prototyping process. It uses the same engineer's experience together with computer simulation methods to create virtual prototypes. This leads to much smarter physical testing and greatly reduces the scope of testing that's required. It increases the likelihood of getting to market faster. Rather than the loop being made of fix-it guesses, it comprises what-if scenarios, which lead to increased innovation. The best news is that a very large percentage of manufacturing companies today, especially the small and medium businesses, have not yet implemented simulation into their design process. This untapped potential represents a very large opportunity for you. In summary, the answer to the question, why simulate, comes from the tangible benefits that are derived. These include eliminating unnecessary cost, which is driving excess out of every aspect of your design. Remove uncertainty from your timelines. Ensure that your product development process is efficient and get products to market faster. Improve quality and customer satisfaction. This tool helps you have a better understanding of how your product functions and helps you reduce defects and deliver higher quality. Reduce unknown risks. Simulation limits your exposure to failure and liability issues. And finally, secure competitive differentiation. Ensure that your employees have the tools to develop innovative products that keep you ahead of your competition. Now that you understand what simulation is and why companies are using it, let's look at the types of problems that can be solved with Autodesk simulation, again with a specific attention on the Nastran InCAD solution. Autodesk offers a wide range of products that cover 5 distinct engineering simulation disciplines. mechanical, CFD, plastic injection molding, composites, and building structures. While CFD, or computational fluids, plastics, composites, and building structures are important, they won't be our focus today. For the purpose of this session, we will concentrate on mechanical simulation as a discipline, not to be confused with the Autodesk Simulation mechanical product. And specifically, we will look at how mechanical simulation can be handled via the Nastran InCAD solution. This discipline represents by far the largest opportunity for you, our manufacturing partners, and it's an excellent fit for your Inventor customer base, and also competing CAD products such as SolidWorks. The discipline of mechanical simulation is a rather self-explanatory term. Engineers use this type of analysis to examine the physical performance of their mechanical designs and see how much stress is created by forces and deflections. Included with mechanical discipline are dynamic and transient loads, which just mean that they can vary position, direction, or magnitude over time. Most products are subjected to this type of condition during normal use. It's also important to understand, for example, how much a design will vibrate and deflect, or its reaction to seismic loading. Engineers also need to determine how long a product will last when subjected to repeated loading. This is known as fatigue life. Another concern of mechanical designers are problems that arise due to heat. Most materials will expand when heated, however, they do not all expand at the same rate. This difference can cause very high stresses and lead to failure, especially when two different materials are fastened together. This phenomenon is called thermal stress, which is also part of mechanical simulation. All of the capabilities which I've just discussed are included with Nastran InCAD. Users of Nastran InCAD can answer critical questions about the performance of their design. For example, will my part bend? If so, how much? Will it break? When will it wear out? Does it vibrate too much? How hot will it get? Can I use a different material? Every product is subjected to some type of mechanical loading, so your potential customer base is very broad. Here we have listed some typical industries that commonly need mechanical simulation. When talking with customers, you should inquire about the performance criteria that they are required to meet and the methods that they are currently using to test and validate designs. Drop tests, pressure testing, vibration, strength, and fatigue experiments are costly and time-consuming, which is a very compelling reason for them to incorporate mechanical simulation into their process. To learn more about Nastran and mechanical simulation, please look for these courses on Autodesk Learning Central. Additional sales material for Autodesk Nastran InCAD and our entire simulation portfolio is available on One Team Source. The easiest way to find it in OTS is to select the Industry tab, scroll to the Manufacturing listing, and choose Simulation. We hope you enjoyed this first introduction to mechanical simulation with a specific focus on Autodesk Nastran InCAD. Please continue and join us for the second session in this series to learn more about how to sell Autodesk Nastran InCAD.